The last lecture we looked at two important notions, namely linear independence and linear dependence. These are very important notions in the study of vector spaces. We also looked at the notion of a spanning set. One important property of linearly dependent set that we found was that if K is a linearly dependent set in a subspace W of a vector space V, then by our scanning from the left, we saw this process towards the end of the last lecture, scanning process from the left. Let us take the linearly independent set to be finite. Suppose we have a finite linearly dependent set K, then by our scanning process we can remove lot of unnecessary information and get a subset K 1 in K such that K 1 is a linearly independent set and the subspace spanned by K 1 is the same as the subspace spanned by K. So, what this says is that if you have a linearly dependent set, you can remove the redundant information and get a smaller set and generate the same subspace that we had. We shall be using these properties repeatedly. Now, the question about spanning set. What is a spanning set? A spanning set is a subset of the subspace W such that every vector can be expressed as a linear combination of these vectors. Now, the question is, should every subspace have a spanning set? Should every subspace have a spanning set? We are not sure about this, and because we have nowhere proved that a subspace should have a spanning set. Now, let us look at this question. Suppose you have a vector space V and we have a subspace W. So, we have V is a vector space, we assume that it is a vector space over a field F, and W a subspace of V. Now, we can think of W as a subset of W itself. Then what is LW? The subspace spanned by this set. We know that LW is the smallest subspace containing W, but W is already a subspace and therefore, LW is indeed equal to W, and therefore, we can think of W as a subspace as a spanning set for itself. We can think of W as a spanning set of W, and therefore, there is at least one spanning set for every W. There is therefore at least one spanning set for W. But are we satisfied with this spanning set? What is a spanning set? A spanning set is like a sampling set. So, it is like a sampling set. What do we mean by this? When we say sampling set, it means that by knowing these vectors in the spanning set, we can generate all the other vectors in the subspace. So, when you have a sampling set and you want to take W as a sample for itself, then we are sampling all the vectors and it is not a very good sampling. Therefore, from the point of view of sampling, our sampling set or the so called spanning set must be a subset of W. So, would like spanning set to be a subset of W. Now, if that spanning set is linearly dependent, that means he has a lot of redundant information and therefore, we would be doing oversampling. Hence, a linearly dependent spanning set is like a oversampling set. And we would like to avoid oversampling because we want to do minimal sampling. Hence, we would like to have non-redundant information only. That means, we would like to have a linearly independent spanning set. This leads us to the notion of a basis. So, we give a definition now. Let V be a vector space over a field F. Let W be a subspace of V. Then a subset B of V of W, a subset B of W is called a basis for W if 1 we want it to be linearly independent, that is non-redundant information, and it should be a good sampling set. That means, it must be a spanning set. That means, the space spanned by Ls must be equal to W. We have used the notation B. So, we will call it as B. L of B must be equal to W. What does this mean? That is, every W in W can be expressed as a linear combination of finite number of vectors, in B. So, that makes it a good sampling set. We do not have redundant information, and by looking at them we are able to take about all the vectors in W. So, basically therefore, there are two requirements. The two requirements for a basis, we repeat, are the following. So, the two basic requirements, one is linear independence and the other is spanning, that every vector in W is a linear combination of these vectors. Therefore, a subset S of W will fail to be a basis if at least one of the above conditions is violated. If at least one of the above conditions is not satisfied. So, therefore, for example, a basis may a subset may fail to be a basis by not satisfying condition 1, that means by being linearly dependent, or it may be linearly independent, but may fail to satisfy the second condition, namely spanning. So, or possibly it is neither linearly dependent nor spanning. What is important is it will fail to be a basis if at least one of the conditions is not satisfy. As of now, we are not sure whether a vector space will have a basis. So, we do not know yet. So, this we will call it as a remark. We do not know yet whether a subspace of the V will have a basis. Now, we must remember that V can be thought of a subspace of itself, and therefore, we can talk of the notion of a basis for V, and therefore, we do not know yet whether V has a basis. We shall make a remark about this question a little later, but to begin with, let us look at some examples. The first example that we see, let us look at F3. Now, in this, where F is a field, we can take F to be R, then we get R3, we can take F to be C, we get C3, and so on and so forth. So, let F be any field and look at F3. What is F3? It is the set of all vectors which are of this form x1, x2, x3 column vectors, such that the entries are all from the field F. Now, in this, consider the vectors E1, E2, E3, the set B consisting of 3 vectors, where E1 is the vector 1 0 0, E2 is the vector 0 1 0, and E3 is the vector 0 0 1. Then clearly B is a subset of V such that 1 B is linearly independent, 2 B spans V, that is LB is equal to V. Why is LB equal to V? Because any vector x is equal to x1, let us look at this, because x belongs to double V implies x belongs to F3, because our V is now F3, which means x is of the form x1, x2, x3, where these xj's are in F. This means x can be written as x1 E1 plus x2 E2 plus x3 E3, which means x is a linear combination of E1, E2, E3, and therefore, every vector is a linear combination of B vectors, and B is already linearly independent. Hence, B is a basis for F3. Similarly, instead of F3 we can take Fn. For Fn we can take B to be E1, E2 etcetera En, where Ej is the vector which has all the components 0 except the jth component which is 1, all others are 0. Do this for j equal to 1 to n, we get n vectors. So, if we take B to be equal to E1, E2, En, where Ej's are this, then this is a basis for Fn. As the next example, let us consider V to be the set of all m by n matrices whose entries are from the field F. In particular, for simplicity, first let us consider V to be F 2 3, that is all 2 by 3 matrices. Then we are going to look at a set B which consists of the following matrices A 1 1, A 1 2, A 1 3, A21, A22, A23. All these A's are matrices, and what are they? A11 is the matrix 2 by 3 matrix which has 1 in the 1 1 place and 0 elsewhere. A12 is the matrix which has 1 in the 1 2 place and 0 elsewhere. Similarly, we have A13 is 0 0 1 0 0 0, it has 1 in the 1 3 place. A21 has 1 in the 2 1 place, A22 has 1 in the 2 2 place, and A23 has 1 in the 2 3 place. So, we have these 6 matrices, and consider these 6 matrices and call this collection of these 6 matrices as B. Then 1, B is linearly independent. It is easy to see this, easy to check this, and LB is indeed F23. What do we mean by this? We want to show that every matrix in F23 is a linear combination of these B vectors. So, because A belongs to F23 implies A is of the form A, B, C, D, E, F, because it is a 2 by 3 matrix, where all these A, B, C, D, E, F are in the field F. Now, that says I can write A as A into A11 plus B into A12 plus C into A13 plus D into A21 plus E into A22 plus F into A23. That says A is a linear combination of B vectors. That means A belongs to LB. That is, every vector in F23 is a linear combination of this. So, therefore, we have LB is also V. LB is the V in this case, the space of matrices. Therefore, B is linearly independent, LB is V, and these are the two requirements for a vector space to be a basis, and therefore, B is a basis for F23. Analogously, if we now consider all m by n matrices over the field F, then consider B to be the collection of all the matrices A I j, where I 1 to m, j 1 to n, so many matrices. For each I and j we get one matrix, where A I j is a matrix which is m by n, which has in the ith row and the jth column, that place 1 and all others 0. Ith row and jth column entry is 1, and do this for every I and j, then B is a basis for F m n. The next example we will consider is that of the polynomials. Let us look at the set of all polynomials over x over the field F, in a variable x over the field F. So, this is the set of all polynomials in x, polynomials in the indeterminate x with coefficients in F. Let us consider this space, and now consider B to be the following polynomials: P0, P1, P2, etc., Pn, etc., etc., where P n x is x to the power of n. So, P naught is 1, P 1 is x, P 2 is x squared, P 3 is x cubed and so on and so forth. Now, this is an infinite set. We have already seen that B is linearly independent and every polynomial is obviously a linear combination of a finite number of B vectors. That is, if P belongs to V, that means P belongs to the polynomial space. Therefore, P must be of the form A naught plus A 1 x plus A 2 x squared plus A k x to the power of k, polynomial, say degree is k, it must be of this form where the edges are all in F. This immediately says that P is A naught P naught plus A 1 P 1 plus etcetera A k P k, which means P belongs to L B. And therefore, every vector in V is a linear combination of a finite number of the vectors in B, and therefore, B is a basis for B. Now, in this space, consider the following subspace, that is, in the space of polynomials we are going to look at a small subspace. Let us say W, I denote it by f e x. It is the set of all polynomials which have only the even powers of x, that is, the polynomials belonging to f of x such that P x is of the form A naught plus A 1 A 2 x squared plus A 4 x to the power of 4 plus etcetera plus A 2 n x to the power of 2 n. So, it has only even powers of x, and that is why we call it f e x, and this is a subspace, and for this subspace 1 x squared x to the power of 4 x to the power of 2 n, the polynomial of the even powers of x is a basis for W, because they are automatically linearly independent, because they are subset of a linearly independent set. So, therefore, linearly independent, and as we have seen above the definition of P, every P is a linear combination, and that too a finite number of these give rise to any P, and hence B is a basis. So, thus we have this important notion of basis, but we should keep in mind that we are yet not sure whether every subspace should have a basis and whether every vector space is a basis. But we should remember again that the two important requirements for a subset S of a subspace W, W is a subspace of B. So, the two important requirements for a subspace S of W to be a basis for W are, what are these two requirements? One, S must be linearly independent, and two, the linear span of S must be equal to W. That is, every vector in W must be a linear combination of a finite number of vectors in S. Okay. Now, we are going to look at view basis from a different point of view. Consider now a vector space V. Now, we will introduce a notion called a maximal linearly independent set. So, let us say W is vector space over F and W subspace of V, and then we say S, a subset of W, is a maximal linearly independent set if one, there are two adjectives in this. One, it must be linearly independent, so linearly independent, and two, we have used the adjective maximal. What does maximal mean? It means that you cannot embed it any other bigger any other bigger linearly independent set. That is, S is not a proper subset of any other linearly independent set. We can state it also like this, that is, if S is a proper subset of S1, which is of course is in W. So, if S is a proper subset of S1, then S1 cannot be linearly independent, that means S1 is linearly independent. So, any set which encompasses S in W must be linearly dependent. So, the moment you try to make it bigger, it loses linear independence. So, that is in a sense a maximal size you could reach for linear independence, and the moment you try to blow it up, it loses its linear independence. So, we have this notion of maximally linearly independent set, that is a set which is linearly independent and which cannot be embedded as a proper subset of any other bigger linearly independent set. Now, let us consider W, the subspace, and let us say B is a basis. Suppose B is a basis for W. Now, consider any set in B which is bigger than W. So, let B1 contained in W be such that B is a proper subset of B1. Now, B is a proper subset of B1, and therefore, there must be a vector x in B1 which is not in B. So, there exists an x which is in B1 not in B. So, let us call that vector x. Now, since x is in B1 and B1 is a part of W, we have x belongs to W. Now, x belongs to W and B is a basis. We have started with a basis for W and B is a basis. Now, B is a basis for W. It has two properties. One, it is linearly independent. The other one is that it spans W. Now, first we shall exploit the property that it spans W. That means, any vector in W is a linear combination of B vectors. So, hence x can be written as a linear combination of a finite number of vectors. Finite number of vectors in B. Say the finite number of vectors are u1, u2, ur. What does that mean? That means x is equal to some alpha 1 u1 plus alpha 2 u2 plus etcetera plus alpha r ur. Now, this says that alpha 1 u1 plus alpha 2 u2 plus alpha r ur plus minus 1 times x is theta of the vector space. This says that there is a non-trivial linear combination of these u and the x vector which gives the 0 vector. It is non-trivial linear combination because the coefficient of x is minus 1. So, therefore, that says u1, u2, ur, x is a linearly dependent set. Now, where is this set? The vectors u1, u2, ur are all in B, which is also B is itself is in B1 and this is also in B1, and therefore, these vectors are all in B1 and therefore, u1, u2, ur x is a linearly dependent set in B1. The moment a set has a linearly dependent subset, the whole set must be linearly dependent. So, therefore, B1 is linearly dependent. So, what have we concluded? We started with a, let us go back, we started with a basis and then we looked at a set bigger than the basis and then we showed that must be linearly dependent. So, what it says is that B is a basis, hence the conclusion is the following: B is a basis for W and B is a proper subset of B1 which is in W, implies B1 is linearly dependent. This means I am not able to embed B in a bigger linearly independent set, which is precisely what is meant by saying B is maximal linearly independent, because it is a basis, it is linearly independent, and we have seen just now that you cannot put it in a bigger linearly independent set or anything bigger than that is linearly dependent. So, we have the first important observation that B is a basis for W implies B is a maximal linearly independent set in W. Now, let us look at whether the converse is true. Conversely, let B be a maximal linearly independent set in W. So, here is W and here is B, which is a maximal linearly independent set. We want to claim that B is a basis. Now, how can B fail to be a basis? So, suppose not. That means B has failed to be a basis. Now, B will be a basis if it satisfies two requirements. One is linearly independent, the other it spans the W. Therefore, the failure of the basis can take place due to two reasons. One, because it fails to be linearly independent, or B fails to be spanning W. Now, B is already given to be a maximal linearly independent set. So, it cannot fail to be linearly independent, because already linearly independent. So, therefore, the only way B can fail to be a basis is that it does not span W. Therefore, since B is linearly independent, the only way B can fail to be a basis for W is by the span being not equal to W. So, that means the LB is in W, but not equal to W. So, let us now take LB. Now, LB is a subspace of V, it is sitting inside the subspace W, and B is linearly independent set in LB. These two we observe. because now L B is a subspace by itself and B is sitting inside, L B. So, B is a linearly independent set in W, but now we have got L B is not all of W, and therefore, there is some vector. Let us draw the picture again. So, here is W, here is B, here is L B, and L B falls short of W, because we assume that B is not a basis, and therefore, there is a vector x in W which is outside L B. So, x, there exists x in W such that x does not belong to L B. Now, B is a linearly independent set. This B is a linearly independent set in this subspace, and x is outside that subspace, and therefore, B together with x will still be a linearly independent set in W. We have seen this before. So, therefore, B is a linearly independent set in L B which is contained in W, and x is outside L B, but in W. Hence, B union x is a linearly independent set, which means B is a subset, proper subset of the linearly independent set B union x, and therefore, B is not a maximal linearly independent set, is not a maximal linearly independent set in W, because we have embedded it in a bigger linearly independent set. But we started with a maximal linearly independent set. We said let B be a max. Remember, we started with the fact that B is a maximal linearly independent set in W, and hence it is a contradicts. This is a contradiction because we started with a maximal linearly independent set B, and therefore, our assumption that B is not a basis is false, and hence our assumption that B is not a basis is false. So, the conclusion we get now is the converse conclusion. We have that B is maximal linearly independent set in W implies B is a basis for W. Previously, we showed that if B is a basis, then it is a maximal linearly independent set. Now, putting these two together, putting by the two conclusions, by these two conclusions, we get B is a basis for W if and only if B is a maximal linearly independent set in W. So, this is a very important observation about basis. In other words, it is a sort of optimal size for a optimally sized linearly independent set. It is optimally sized sampling set, because it is going to span the whole space. So, it is this property, you will just make a note, we will not prove this, it is this interpretation of a basis together with what is known as the Zorn's lemma that assures us that every vector space has a basis and therefore, every subspace of a vector space has a basis. We will not go into the proofs of these statements using John's lemma, we will take them for granted. Now, let us look at some examples again. Let us look at F3 and we had the basis be E1 1 0 0, E2 0 1 0 and E3 is 0 0 1. We already seen and it is very easy to see that B is linearly independent. Now, suppose B1 is any set in F3 such that B is contained in B1, but not equal to B1, that is B is a proper subset of B1. Therefore, there exists an X in B1 minus B, call this as X1, X2, X3 and we have X is equal to X1 E1 plus X2 E2 plus X3 E3 and that implies that E1, E2, E3, X is a linearly independent set, all of them are in linearly dependent set and all of them are in B1 and therefore, B1 has a linearly dependent set inside it and therefore, B1 is linearly dependent, which says that anything bigger than B is linearly dependent and it is already linearly independent B and therefore, B is a maximal linearly independent. So, that we see that a basis has to be a maximal linear independent set. Now, let us look at the example of the matrices. Let us for simplicity look at F2 by 3, the set of all 2 by 3 matrices. When we are looking at all the 2 by 3 matrices, we had these matrices A11, A12, A13, A21, A22, A23. Remember these matrices, A11 has 1 in the 1 1 entry and 0 elsewhere, A12 has 1 in the 1 2 entry, 0 elsewhere. In general, Aij has 1 in the ith row jth column and all other entries are 0. Then B is linearly independent and B1 contains B means there exists a matrix which is in B1 which is not in B and let A be a 2 by A B C D E F and as we have seen before A can be written as A11 plus B A12 plus C A13 plus D A21 plus E A22 plus F A23, which means the matrices A11 up to A23 and A are linearly dependent and these are all in B1, that says B1 is linearly dependent. So, what we have is B is linearly independent by 1 and B cannot be embedded in a linearly independent set or anything bigger than B must be linearly dependent, which is what is exactly meant by saying that B is maximal linearly independent. Let us now look at the example of the polynomials. Let us look at f x. Then we had the basis 1 x, x squared etcetera x to the n recall we called P n as x to the power of n. Okay. So, the basis we can also write as P naught, P 1, P 2, P n, etc. Now, again as we have seen earlier many times, B is linearly independent in V. 2, suppose we have a set bigger than B 1 in V, and again therefore, there must be somebody in B 1 who is not in B, they are all polynomials. So, there exists a P in B 1 minus B, and since P is a polynomial. So, let P be equal to A naught plus A 1 x plus etcetera A k x to the power of k, and that says P is equal to A naught P naught plus A 1 P 1 plus A k P k. Now, this says P naught P 1 etcetera P k P are all linearly dependent in B 1, and therefore, B 1 is linear. If you set has a subset which is linearly dependent, the whole set must be linearly dependent. Therefore, B 1 is linearly dependent, and therefore, anything bigger than B is automatically linearly dependent, and hence B is maximal linearly. Thus, we see that the basis is maximal linearly independent. Thus, the notion of a basis is in a sense an optimal sampling set. Okay. So, let us recollect that this is the most important aspects of basis. You can interpret it as a linearly independent set spans. Basis for V means spans V. So, basis for W means it is linearly independent W and spans W. Basis for V means linearly independent set in V and spans V, or we can look at it equivalently as a maximal linearly independent set in W. However, recall that our idea was getting into a basis was to get an optimal or a reasonably meaningful sampling set. If you now look at the example of the polynomials, even though we got to this notion of non-redundant minimum requirement for spanning the space, the set B we got 1 x, x squared etcetera is an infinite set. So, we still have to deal with in certain vector spaces an infinite sampling set. The easiest cases are those, or the simplest cases are those where we can get finite basis, because then we have a finite sampling set. So, this leads us to the notion of finite dimensional subspaces. We have not yet introduced the notion of the word dimension, but we will come to it shortly. Finite dimensional spaces. So, let W be a subspace of V and let W have a finite basis. So, we have a subspace which is having a finite basis, then we say W is a finite dimensional subspace. If V itself has a finite basis, we say V is a finite dimensional vector space. So, we have the notion of a finite dimensional vector space and a finite dimensional subspace. We will be dealing mostly with these finite dimensional spaces in this course. Now, let us look at a finite dimensional space. So, let V be a finite dimensional vector space. What does this mean? This means there is a finite basis. So, let us call it, let it be u1, u2, un. Suppose there are n vectors which form a base. What does this mean? These u1, u2, un are vectors in V, they are linearly independent and they span V. That means, every vector in V is a linear combination, that is u1, u2, un are vectors in V, they are linearly independent and they span V. This is what we mean. Span V means everybody is a linear combination of these u1, u2. Now, suppose I have another set which has n plus 1 vectors. So, I have a basis which consists of n vectors. Now, I am looking at any set which has n plus 1 vectors. Our claim is the following: we claim B1 must be linearly dependent. Why is this so? Suppose not, then B1 is linearly independent. Now, look at, we have all these vectors u's, we now append the vector V1. Since u1, u2, un is a basis, V1 can be written in terms of u1, u2, un, and therefore, V1, u1, u2, un will be linearly dependent, since V1 is a linear combination of u1, u2, un, since B is a basis. B is a basis, everybody must be a linear. Now, we have seen last time that if we have a linearly dependent set, you can knock off redundant information from scanning from the left and get a subset which still spans the same space. Now, when we scan this B1, u1, u2, un by from the left, first we will be looking at V1. We cannot knock off V1 because V1 alone is linearly independent, being a part of a linearly independent set B1. So, we can't knock out V1. So, we will be knocking out some of the u1s. So, what we will get is, by scanning from left, we get, let us call this set as S1, we get a set B1 which will have V1 and a part of this B, we will call it B11, where B11 is contained in B, and therefore, which is spans same space as S. So, therefore, we have LS is equal to LB1. But if you look at LS1, the LS1 already contains u1, u2, un basis vectors who already span the whole space V. So, LS1 will be V. So, LB1 will be equal to V, because LS1 is V, since u1, u2, un basis vectors are already in S. So, we have got a subset of B1 together with V1 which forms a basis. Now, what we do is, we will look at appending V2 to this and then apply scanning. As before, we get V2, V1, B21. Another set, we will call it as B2, which spans again V. Continuing this way, we will knock off the vectors of u at each stage, at least one will be knocked out. So, at the rth stage we would have got V r V 1, V r V r minus 1 etcetera V 1, and we would have knocked off all the vectors from V 1 span V, and since each stage we knock off one u vector, maximum stage we require is r less than or equal to n, and therefore, we have V r V r minus 1 V 1, they are part of a linearly independent set and they span V, and therefore, they form a basis for V. Since they form a basis for V, any vector must be a linear combination of them. In particular, therefore, V n plus 1, which is out none of these fellows, is a linear combination of V r minus 1 V n, which means that V 1 V 2 V n plus 1 must be linearly independent, must be linearly dependent, because V n plus 1 is a linear combination of the previous fellows, this must be linearly dependent. This is contradiction, because we started with the hypothesis that suppose B 1 is linearly independent. So, therefore, this is a contradiction, and hence we must have B 1 must be the set consisting of this V 1 V 2 V n plus 1 must be linearly independent. So, the conclusion that we have from this is that if V has a basis having n elements, then any set having n plus 1 elements is linearly dependent. This is a very important property. Using this property, we will be able to show that once a vector space has a basis consisting of finite number of vectors, then all bases will consist of finite number of vectors and all bases have the same finite number of vectors. This will lead us to the notion of dimension, and we shall look at these aspects in the next lecture.